所有东西要放在一起。为什么这个很小？
少用的多，一个空里边
没选。
得用 MDP。
我们没法比这个高。我reinforcement。到挺下面。
现在是9号，还有1个月是吧？
有一个3那个 OM 招那个 recruitment 的，那个卡住了。
没有什么 recruitment。
对呀，有 repeat 吗？
不是 recruitment。现在没有 recruitment。
应该呀，接 S 招是吧？
不是主要招哪个？
咱看不上，他只要那个卡后鼻。
Good morning, everyone. Last time we gave the motivation for considering solving a problem by block. That's the algorithm we are going to introduce is a randomized block coordinate descent. So instead of solving, so here the x is in high dimension, and here could be 1 million or several millions. So the way we solve this problem is not by taking the full gradient. We do not do full gradient computation or taking directional derivative, because that will take every iteration, the computation will be on the order of n, and that is too expensive. So we block the long vector into a few pieces. Right here we call it B blocks, and every time you just update randomly choose one block and do the gradient method, update one block. So this is the basic idea. The setup is as follows. So we consider again the composite optimization structure. We minimize f plus h. I will tell you what's the specific structure of f and h would be. And here let's consider this the decomposition of this identity matrix. This is an n by n identity matrix. We break it into, just by columns, we break it into B blocks. So every UI is in dimension n by ni. So the number of rows is n for everyone is n, but this one has n1 columns, this one has n2 columns, and all the ni's sum to n. Okay, so this is a decomposition of the identity matrix. With this decomposition, we can also decompose the long vector. We decompose this long vector also into B blocks. So you can re-represent this vector using this decomposition matrix UI. So UI times xi, this is in the dimension Rn, right? Because this is Rn by ni, this is ni. So this is Rn vector. But this is only non-zero in the ith block, right? This is, so UI times xi, this is again a long vector in Rn. But only the ith block is non-zero. Others are just zero. Right? So this summation is just breaking the long vector into B pieces, just like what we do here. Right? Every time when you do this multiplication, you just get the ith block is non-zero. Others are just zero. And when you do the summation, you just fill in all the blocks. Okay.
So if n is 3 and x is 1, 2, 3, this x1 is just 1, 0, 0, 0.
It depends on how many B's you have.
Okay.
Right.
Okay.
Then what is the dimension of xi?
Xi is in Rn. Xi is the block here, right? In total, you have m elements, right? Each xi just takes the ith block is just ni elements here. You see this idea? So this is the x. For example, we break it into 4 blocks. This is your x1, x2, x3, x4. Right? UI, for example, U1. U1 here, maybe 1, 1, 1, 1, and 0. Right? Because this is taken from this it's taken from the identity matrix. It has all the ones on the diagonal, but we just take the first block. Right? If you do this multiplication with some xi, then the multiplication is like you just have x1 here, but others are 0. Right? That's the idea.
The size of x1 and x2 are not the same necessarily.
They are ni, they can be different. Depends on the decomposition that you chose for your identity matrix. Okay, and this is the reason why we want to do this computation block by block. It's not only for the computational efficiency, but also it's because of the nature of large-scale computation. So the data may be distributed in different clusters, computers, or it can also be distributed in time, right? So some information may not be available anytime. So for example, this block of information may be only available at a certain time. So you can only access this information when it is available. But before that, you may only be able to update other blocks, right? It's because of the nature of large scale computation. The data may be distributed either in space or in time. Okay, now let's talk about the properties f and h should possess. First, for h is closed, convex, simple. Simple just means its proximal mapping is available to us. And also it's separable. Separable means the function can be decomposed also into B blocks. And each block, the argument is just the xi for the ith block. Okay. And simple means for every hi, we have a proximal mapping. So H is very special. For f, we assume it's closed convex and also differentiable over the domain of h. Moreover, we assume some smoothness about f, and this is like a blockwise smoothness condition. Here you can see from x, we only do an update in the ith block, right? So we consider 2 points, x and the x bar, but we do not make the assumption on the whole vector. So the smoothness is not for the whole vector, but it's only for the ith block here, right? This is like an update from x to x bar, and this is a linearization But this linearization for the inner product term, this is only taken for the ice block. And this is also the distance between the two ice blocks. Okay, so here, this is basically equivalent to, so let's call this point as x hat. Okay, so this inner product is equal to and this distance is also equal to x hat minus x. Right, so all the updates are happening in the ice block. And here, number I just means so first you take the gradient of f and then take the ice block. Okay, all these objects are in the space Rni. Okay. So in the algorithm, we are going to use this smoothness parameter Li for the ice block instead of using the smoothness L for the whole block, for the whole gradient, the full gradient. Let me first introduce the update in the ice block. Suppose we are given the previous iterate x0 and given the subsize lambda I for the ice block. Then this is the ice block update. This is the gradient method applied to the ice block subproblem. Right, here is basically it's the linearization. Well, I skip the constant here. This is the same as what we have here, right? In the product for the ice term. UI here is the variable, is the discrete variable. And here we only take the ice block for the h function because it's separable, right? So we don't care about other hi's, only the ice block component. And this is also the prox term for the ice block. Okay, because we have the prox mapping for hi, so this subproblem has a closed form solution. With this, we can define the algorithm. And also, this is the result for the ice block. So the update for the whole, the full X. So you also need to have an update for the full X, right? We are going to use this UI to define the new update for the X. So let's call this as XI. I just means we only update ice block. Right, this is the update we have in the ice block, and multiply it with UI. You make this, turn this n by ni vector to be an Rn vector, and then add it to the xi. So this is a change we have. This is what we were at. Plus, to this summation, you have the new search point xi. Right, this is in Rn space.
It's more like a blockwise proximal gradient descent.
Right.
The shape of UI is not clear for me yet.
UI is
Like a diagonal.
no, UI is it's this matrix. It's a tau matrix.
And it sweeps over.
This is the identity matrix. The whole thing is the identity matrix. UI is just a few consecutive columns of it.
Does the distribution matter here?
Yeah, it matters.
Okay.
But here, let's just assume it's a general one. So the algorithm is simple, quite similar to the proximal gradient method, except that we need to generate a random variable. This is to decide which block you want to update, right? So for the case iteration, we want to generate a random variable, which is, this is ik is among this ik is in the set 1 to b. Generate a random variable from 1 to b according to this distribution. This is just a probability mass function. Okay, but pi is undetermined here. after generate this random variable ik, we're going to update the ik's block using this update. Okay, so that's why it's called randomized block coordinate set, because we are doing the block-wise coordinate update, and also it's a randomized algorithm. The problem is not random, it's not stochastic, but it's just the method is randomized. Okay, we artificially introduce this randomness here.
Why is this not that expensive? Like for each block, you indeed reduce the dimension, but here you generate a random variable. So when you stop, perhaps you do. Can you guarantee you do less than what you were supposed to do? For instance, if I choose the probability to just be 1, you always choose I equals to 1. Then you always update the first block. So you never stop because you can't update other blocks.
It could happen, but first of all, that probability is not, it's an ill-posed probability. Well, if it happens, for example, if it's not 1 for the first block, but it's just some arbitrary distribution, but it just happens you update the first block all the time. But in expectation, the algorithm still works.
Okay.
What we want is an expectation result, yes.
Can you change the distribution over time? Or is it time homogeneous or?
It might be possible, but I haven't studied that. I just fixed this P, this probability mass function at the beginning of the algorithm. Let me see. In the end, the convergence guarantee. In the end, the convergence guarantee is something like the expected value phi of xk.
Same as the proximal gradient, the convexity.
It's similar. It's on the same order, right?
Yeah, same order.
Suppose this Li is some L. They're the same, right? We can factor out this L and B times this L tilde. B times this L tilde is similar to the L for the full gradient. In the end, the order is the same, but so this gives you the convergence rate similar to what we have for the full gradient update. but every time you just need to update an I dimension vector. So
Yeah.
this is cheap. Per iteration, it's cheaper.
Yeah, it's quite impressive.
Yes.
But because you have the factor b there, you still have to do b times as many iterations. So if each block is the same size, then you're doing the same amount of computational work per whole vector update on average.
And B is time. So yeah, the question is whether this is true or L tilde is similar to L. Can do this computation. See. Okay, this is, let's consider square. The square is summation. Okay, this is not right. What we have is L tilde is on the order of L, right? So here you can see this L should be something no more than max of Li, right, from this computation. So in principle, this should be smaller than if you just use L times x0 minus x star, right? Because here you are using the yeah, this is like the max, but here this is not the oh no, yeah, you are right. This is multiplied by b. Right. This does not give you an acceleration like for the for a factor of b. You do not gain that acceleration. Yes, that's right. Let's compare. We can compare. Just compare these two. So the conclusion is for the randomized algorithm, the complexity will be for the other one. Right, and here for every iteration we do an I update, and here we do order n operation. Yeah, so in the end, these two are on the same order. We do not gain anything here. But the good thing is that the computation here is really in Ni dimension, because in many cases you do not have the full dimension information, right? And also, I remember I did some calculation a long time ago. Here, if you do it very carefully, you can compute a quantity that is similar to this L, and you can show there is a subtle difference between the two. Here is more or less like some kind of average. I don't remember the name of this average, but for example, there's this average, right? You can have this kind of average and compare this average with the other one, with the L. Right? This one should be smaller than the other one. Somehow you can, from this computation, you can show this kind of average. Use this one as an approximate full gradient smoothness parameter. This should be smaller than this one. Okay. Yeah, so we do not gain anything in the order of B, but the computation in each iteration will be easier. And also, okay, so the one I just erased, the benefit also happens when the LIs, the local LIs are small, right? The smaller they are, the more benefit you are going to have.
So does that, just with that averaging, does this mean that this is favorable for very ill-conditioned functions? So if you have some dimensions that are...
Yeah, that's right, yes. Yeah. So this is more like a localized smoothness parameter, right? For some blocks, you really have a small Li, so you do not want to use the overestimated L for the full gradient. That is not suitable. Right? Just like the case where we do adaptive method. Remember in natural acceleration, we mentioned some adaptive idea that you do not use the L. So in that case, we use the L for any pair x and y in the domain of H. That could be very conservative, right? If you use some local information for the local x and y, that will be the L you're gonna use is smaller, and the convergence rate is proportional to L, right? So it's faster. So here is the same idea. It's not a localization for the points, but a localization for the blocks. For some block, the Li is very small, and comparing this, the average I just defined is much smaller, right? Using that average than using this global estimate L. But you are right, we do not gain any factor in terms of B.
Even with that L you erased.
Right, we don't gain a factor of B, but just the local L will be small. The local LIs will be small for a certain block. Okay, let's do the convergence analysis for that algorithm.
尾。
The first lemma is for the updating the ice block. If you apply the randomized block coordinate descent to the ice block, suppose the random variable we chose in a certain iteration is ice block, then this inequality holds. So this x, the previous iteration we were at xi, the next iteration, the full iterate is this xi. So the phi function value difference is lower bounded by this quantity. And lambda I is the subsize, Li is the local smoothness, epsilon I is defined in this manner, Ri is defined in this manner. Okay, so this is this part is similar to the one in the IPP framework. Remember, we have something similar to this, right? Usually say this is in the T epsilon, right? In the epsilon enlargement of the mapping T. But here we are not going to use IPP framework to analyze this algorithm. Epsilon I, we also define a function epsilon of something in this way. So this is only a function defined for the ice block. And we also call this quantity as epsilon I. So here, before we do the proof, let's first note some relations relating the local computation to the global computation. Here we should switch the order. This is a local stuff, this is a global, this is also local. Right? These are obvious by the definition because, for example, here, this one we mentioned already over there, and this is by the structure of H, it's decomposable. And also, these two full vector, they only differ in the ice block, right? And this is also by the same reason, they only differ in the ice block. I recall, so the update scheme is what I just erased here, and the optimality condition to that one, it's just that the 0 belongs to the gradient, 0 belongs to the subdifferential of that update function, and it's equivalent to this one if we use a definition for Ri. And also if we do this correction, change this point to x0, then we need to introduce this epsilon subdifferential, and the epsilon I is exactly the epsilon we define here. Okay? And so from here we can also see an equivalent formula for epsilon I. Because x0I minus xi divided by lambda I is Ri. So here, this quantity is lambda I times Ri, right? And so this Ri times this Ri, we get Ri square. Right? Here we have Ri square. And so this is an equivalent formula for epsilon I, right? And moving that term, this term to the left. And we have this relation. I think it's better to write it explicitly. Let's change this to be a global computation. So we use these two conditions to change them to be the global computation, like these two. Okay, this is a global computation, and here we just add and subtract f of x0. This is by definition f plus h is phi. Here it's by the smoothness assumption for the ith block, right? And again here, let's use the last condition here, the connecting global and local. Xi minus x norm square is lambda I square Ri square. This one is Li over 2 okay, and now let's rearrange the terms. We get exactly this one here. These two conditions are not used in the proof. This automatic condition is not used. But let's see. It will be used later, but not here. In the proof, you can skip these two lines. You just do the computation. This proof is just a calculation. Don't need to use automatic condition.
That is the minus the second last line fx0 minus.
Oh, yes. Yeah, that's right. Okay, now we need to define, to facilitate the discussion later, we need to define two new norms. This norm is for the primal, this norm is for the do. Here star means the do norm. This R sharp is defined using the subsize lambda I and the probability pi. So this is the summation for the norms for the ice block. And here this is a general norm. We do not specify what it is in general. So you can also associate it with a do norm. You can check this definition. It satisfies the do norm's definition if you use this one as the do norm. And here is also the do to this general norm. This star is just a do norm. This is the inverse of the whatever you have here, pi lambda I over 2. And in our case, we just simply take this general norm to be the L2 norm, and hence the do norm is also the L2 norm. So here you can just build both of them as some weighted sum of the L2 norms for the ice blocks. if we choose the lambda I as 1 over Li, this 1 over the smoothness as in the normal gradient step algorithms, and then apply the randomized block coordinate descent, what we have is this expectation result, 5x0. So this is just one step of the algorithm. If you start from x0 and do the algorithm, use the randomized block coordinate descent method, what you can say is that 5x0 minus, so x is a random variable. It's like the output of your one iteration of the algorithm. Expectation of the function value of this x minus this quantity is at least the R sharp norm square. So this is the new norm we defined here. Okay. The proof begins from this result. So this is for when the ice block is fixed, but it's still a random variable. We just fix it now. But this I is generated from your PMF, right? Probability mass function. And if you take expectation of that one, you exactly have. So let's first look at this identity. This is just by definition, right? You have B possibilities, right? We are just summing over the B possibilities, averaging out. And this inequality is actually by taking the expectation of that one, right? That one, for the ice case, it holds with probability pi. So you just multiply each inequality with pi and then sum them, right? This is the expectation of that result. And here it's because we take lambda I to be 1 over Li, so you have this identity. And here we just use the definition for the new norm. Okay, so this proves the lemma. Yes.
In the first line, we have inserted the phi of x0 inside the sum and use the lotus. Am I right?
What do you say?
If phi x0,
This one?
yes, we have inserted it into the expected equation.
This is, so suppose x0 is given. This is deterministic.
Yes.
And here, because pi is summed to be 1, right? So this is the same thing,
Yes.
right? And actually, this summation pi 5xi is a definition for this expectation,
Yes.
right? This is just because it's deterministic and pi is summed to be 1. Okay. So this proves the lemma.
So for this algorithm, the initial choice of your blocks is really important, right? You want to you don't want to like mix up some smooth part and non smooth part to make a block that was supposed to be good to now it's a bad block.
What do you mean the first iteration is important?
No, when you choose the does the choosing the block matter here?
How do you divide the blocks?
Yeah.
Oh.
Yeah. You want to.
That's right. That's right.
Yeah.
So you need to take advantage of the LIs.
Yeah.
The way you split the blocks should be based on the LI information.
Okay.
I need to do the calculation again, show you the average smoothness I computed a long time ago. But the idea is to make that one small.
Okay.
Yeah.
Yes. So we have bounds for the expectation. Do we have any bounds on the variance? Or
You can also establish in the end you can also establish high probability results. But it is more involved. If you are interested, I can suggest some papers to you.
Okay, thank you.
But in the class, I will just present the convergence expectation. Because this is just the beginning of the proof. We have a long way to go. Okay, so that one can be viewed as an upper bound on this new norm. Let's develop a lower bound to the norm. Okay, so this is the lower bound. Let me see. Oh, this is wrong. You need to use a do norm. Okay, because R is like the gradient, right? Because R is something, as I mentioned, R is something like your Ri is in some T epsilon I x tilde I. Right? It is like the gradient from the perspective of the initial proximate point framework. Ri is like the gradient, so the do norm should be the distance between the points, right? So this is the lower bound we have for Ri, for the R. And we first need to use optimal condition. The optimal condition is used in this proof, but not in the first lemma. So we start from this inclusion. Starting from here, we have this is just rewriting that inclusion in terms of inequalities. This holds for any UI in ni dimension. Now let's take UI to be the ice block of the minimum x star. And then let's sum over all the blocks. Okay, so here we just sum over all the blocks. And here we are connecting the local computation with the global computation. This is the inner product happens for the ice block. And summing them up, you have the inner product for the full gradients, for the full vectors. Okay. Here we just rewrite the term. From this line to here, we use the convexity of f. And here is, by definition, f plus h is phi. And the last inequality is just by Cauchy-Schwarz for the general norms, right? These are some general, you can view them as general norms, prime and dual norms.
Minus epsilon. Some of
Oh no, plus we put it to the left.
R we also. Oh, I
If you
see.
switch x0 and x star. Okay, and combining the two, we arrive at the conclusion. Right? Here, CK is defined to be the sequence of all the random coordinates we generated before case iteration, right, or until case iteration. So it's a collection of k random variables. And we also define here, because xk is a random iterate, so 5xk is still random, and this is taking the expectation over all the randomness we have, right? This is a total expectation, and this is deterministic, and this epsilon bar k is also deterministic. Xk is random, epsilon is a function on the random vector, so this is also a random number, and this is a total expectation, taking the expectation of all the randomness we have, all the random coordinates. And we also define delta k to be phi k minus phi star. So this is the expected function value gap, expected primal gap, right? Let's do one more proof for one more lemma. Previously, we had the result for one step. We have the one I just rewrote here, erased here. Right, this is what we have for one iteration. And this is, of course, greater than or equal to 0. So this inequality is just a way to rewrite this one here. Right here, x0 is a certain iteration xk, and this is just this is basically a conditional expectation, conditional on all the previous randomness you have, and these are all absorbed into this random vector, right? If you fix x0, then this is expectation for the randomness you just saw. Well, this is actually a conditional expectation, right? And here it's the same idea. Fix xk, you fix all the randomness you have so far, and rewrite this inequality, right? This is just a rewriting. But to take the full conditional expectation, you still need to take the expectation for all the randomness we have previously, and these are all in this sequence. These are I1 to ik, right? Because the one you just see is ik plus 1, and previous ones are I1 to ik. They are all in the sequence ck, right? So we take the expectation for ck, and then if you take expectation for ck and use this definition, right? The expectation of this one is just phi k, and this one becomes phi k plus 1, and here it becomes the total expectation epsilon k plus 1 bar, right? That's the proof. Okay, so far we haven't specified the probability mass function. And next time I will show you when the probability mass function is uniform, pi is just 1 over b, what the final result would be.
So the papers that you went through looking at the with high probability proofs?
So you can search for this one. I just remember the name of the composers. Peter. Something like this, Martin Tucker. You can search for their maybe 2014 paper on mathematical programming.
Okay.
2014 or 2013.
All right, thank you. And also for, I'm guessing it's okay, but for the project, is any just generic coding language okay, like with Python?
Yeah, anything is fine.
I'd like to do C++, but that might be a little painful for me for learning.
Oh, yeah.